Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. In this lecture, we are going to discuss some more properties of trigonometric and hyperbolic functions of complex variables. So first we see the relationship between trigonometric and hyperbolic functions. We can convert hyperbolic function into trigonometric or trigonometric into hyperbolic function using these relationships. So first relationship is sin hyperbolic iz equal to I sin z, and cos hyperbolic iz is equal to cos z. So here I is eliminated and cos hyperbolic z is converted into cos z. Here I is multiplied with sin z. Similarly, for sin iz we have I times sin hyperbolic z, and cos iz is equal to cos hyperbolic z. So we are not going into the proof of these identities, but they can be easily proved using just the definition of all these functions. So we will remember these relationships. They are important to prove further properties of these functions. Another important property is sin hyperbolic of minus z equal to minus sin hyperbolic z. That means sin hyperbolic z is an odd function, and cos hyperbolic of minus z equal to cos z. That means cos hyperbolic z is even function. So like cosine and sine, cos hyperbolic and sin hyperbolic are even and odd functions. We know that cos z is even function, sin z is odd function. So here not only these trigonometric functions, but corresponding hyperbolic functions are also even and odd. For trigonometric functions we have this formula: cos square z plus sin square z is always 1. So for hyperbolic functions that formula is similar to this one, but here instead of positive sign we have negative sign. So cos hyperbolic square z minus sin hyperbolic square z is always 1. So this also can be proved by definition, but we are not going into the details of the proof. This is also property analogous to trigonometric functions. We know that for trigonometric functions we have sin z1 plus z2 is sin z1 cos z2 plus cos z1 sin z2. So this property of trigonometric functions is also true for hyperbolic sin hyperbolic functions. So if I replace this sin function by sin hyperbolic function, then also this property is true. Sin hyperbolic z1 plus z2 equals to sin hyperbolic z1 cos hyperbolic z2 plus cos hyperbolic z1 sin hyperbolic z2. So this we can prove easily using that relationship between hyperbolic sin and trigonometric function. Okay, so we know that sin hyperbolic z is nothing but, we use these relationships. So we can use this relationship: sin iz is equal to I sin hyperbolic z. So we have sin iz equal to I sin hyperbolic z. So from this we obtain sin hyperbolic z is 1 over I sin iz. Now 1 over I is minus I, so it is minus I sin iz, and this is true for all complex number z. So instead of z we have z1 plus z2. So we replace z by z1 plus z2 to find out this sin hyperbolic of z1 plus z2. So here we replace z by z1 plus z2. So we obtain minus I times sine of I of z1 plus z2. So this we can rewrite as sine of iz1 plus iz2. Now we use this property of sine function which we have written here. This property is true for complex sine function. So now we apply that property. Instead of z1 we have iz1, and instead of z2 we have iz2. So sine of iz1 plus iz2 equal to sine iz1 into cos iz2 plus cos iz1 into sine iz2. Now again we use the relationship between trigonometric and hyperbolic functions. I can replace sine iz by I sine hyperbolic z, and cos iz can be replaced by cos hyperbolic z. So we use these properties. Sine iz is I sine hyperbolic z. So sine iz1 is I sine hyperbolic z1. Cos iz2 will be cos hyperbolic z2 plus cos iz1 is cos hyperbolic z1, and sine iz2 is I sine hyperbolic z2. Okay, so using this we are able to write in this form. Now we can see there is a complex number I in both the terms. So if we take it outside we have minus I square, minus I, and 1 I will be outside, and we have sine hyperbolic z1 cos hyperbolic z2 plus cos hyperbolic z1 into sine hyperbolic z2, and negative of I square is minus of minus 1. So we have sine hyperbolic z1 cos hyperbolic z2 plus cos hyperbolic z1 sine hyperbolic z2. So we are able to prove that sine hyperbolic z1 plus z2 is nothing but sine hyperbolic z1 cos hyperbolic z2 plus cos hyperbolic z1 sine hyperbolic z2. Similarly, we can prove this property for cos hyperbolic function also. Okay, so we start with this property. We know that cos iz is nothing but cos hyperbolic z. That means cos hyperbolic z is nothing but cos iz. Okay, so we write in this way. Now we are interested in cos hyperbolic z1 plus z2. So by this property, this is, so cos hyperbolic z1 plus z2 can be written as cos I of z1 plus z2. Now we use the property of cosine function. Cosine of iz1 plus iz2. This I can write as cos iz1 cos iz2 minus sin iz1 into sin iz2. Again, cos iz1 is nothing but cos hyperbolic z1. We are using this property. Cos iz is cos hyperbolic z and we will also use sin iz is I sin hyperbolic z. So cos iz1 is cos hyperbolic z1, cos iz2 is cos hyperbolic z2, sin iz1 is I times sin hyperbolic z1, and sin iz2 is I times sin hyperbolic z2. So using these two properties, so this gives us cos hyperbolic z1 into cos hyperbolic z2, and this is I into I, that is I square, which is minus 1, and minus 1 into minus 1 will be plus 1. So negative negative positive, minus of I square, that is minus of minus 1, which is 1, and here sin hyperbolic z1 into sin hyperbolic z2, and left hand side is cos hyperbolic z1 plus z2. Okay, so you can see there is a change here. In trigonometric cosine function we have negative sign here, but for hyperbolic cosine function we are having positive sign here. So that is from this step. So in this way, if we know these relationships, then it is not hard to prove these simple properties of trigonometric and hyperbolic functions. Next property, sin hyperbolic z can be written as sin hyperbolic x cos y plus I times cos hyperbolic x sin y, or this question can be asked in this way also: find real and imaginary parts of sin hyperbolic z. Sin hyperbolic z. So let us see how to prove this. So we have, so to prove this property we use the relationship between trigonometric and hyperbolic functions. As we have seen, sin iz can be written as I times sin hyperbolic z. So from this we can write sin hyperbolic z equal to 1 over I sin iz. Now 1 over I is minus I, so we have therefore sin hyperbolic z is minus I sin iz. Now we start by taking z equal to x plus iy. So then sin hyperbolic z equal to minus I sin z equal to x plus iy. So here we replace z by x plus iy. So we are using this, and there is no need to give this number 1. Okay, fine. So sin hyperbolic z is minus I sin iz, and we put z equal to x plus iy because we require our answer in terms of x and y. So now this is a trigonometric sine function, and this I can rewrite as I into x plus I square y, that is minus y. I into x plus I square times y, and I square is replaced by minus 1. Now we use the property of trigonometric function. So using that property I write this as sin x cos y minus cos ix sin y. but we require our answer in terms of hyperbolic functions, and we know that sin ix can be written as I sin hyperbolic x. Cos y we keep as it is, and cos ix is nothing but cos hyperbolic x sin y. Okay, we have used this property. Cos iz is cos hyperbolic z, and sin iz is I times sin hyperbolic z, using this property. So sin ix is written as I sin hyperbolic x, cos ix is written as cos hyperbolic x, using this property. Now if we simplify this, we have to write minus I into I, that is I square. I square is minus 1, and minus 1 will be plus 1. So we have sin hyperbolic x times cos y. Similarly, this is minus I into minus 1. So that is going to be I square. So minus I into minus 1, that is I square cos hyperbolic x sin y. Okay, so there is no I here, it is minus sign, and here minus sign, so minus minus plus, so we will have only I here. Okay, minus I into minus 1, that is I. So you can see we are able to prove that sin hyperbolic z is nothing but sin hyperbolic x cos y plus I times cos hyperbolic x sin y. Okay, we are able to prove this. Sin hyperbolic z is sin hyperbolic x cos y plus I times cos hyperbolic x sin y. So real part of sin hyperbolic z is sin hyperbolic x cos y, and imaginary part is cos hyperbolic x sin y. So from this we can determine the absolute value of sin hyperbolic z. Okay, because we are now having real and imaginary parts of sin hyperbolic z. So if we take absolute value, then we have to write square of real part plus square of imaginary part, so which is cos hyperbolic square x into sin square y. Now if we want to eliminate these cosine terms, we can express in terms of sine terms only. Then we replace this cos square y by 1 minus sin square y, and this cos hyperbolic square x can be replaced by 1 plus sin hyperbolic square x into sin square y, because we are using these two relations, cos square x plus sin square x is 1, which is used here, and cos hyperbolic square x minus sin hyperbolic square x equal to 1, which is used here. Now if we simplify this, we have sin hyperbolic square x minus sin hyperbolic square x into sin square y plus sin square y plus sin hyperbolic square x into sin square y. So we can see these two terms will cancel out, and we are left with sin hyperbolic square x plus sin square y, and here we have sin hyperbolic z square. Absolute value of sin hyperbolic z square is sin hyperbolic square x plus sin hyperbolic square y, sin hyperbolic square x plus sin square y. So we have proved this one. Similarly, we can find out real and imaginary parts of cos hyperbolic z, and then we can prove this also. So but I am not going to prove that part. Similarly you can do for cosine and cosine functions. Next property is sine hyperbolic z and cos hyperbolic z are periodic functions with period 2 pi I. So if I want to prove that sine hyperbolic z is periodic function, I have to show that sine hyperbolic z plus 2 pi I must be equal to sine hyperbolic z for all z. Okay, so they can ask in this way also, or prove that sine hyperbolic z plus 2 pi I equal to sine hyperbolic z for all z. Similarly they can ask for cos hyperbolic z also. So first we try to prove for sine hyperbolic z plus 2 pi I. So here also we can use that property. We know that sine iz is I sine hyperbolic z. Okay, we know this property. So we start from this. We know that sine iz is I times sine hyperbolic z. So therefore sine hyperbolic z can be written as 1 upon I, which is minus I sine iz. So therefore sine hyperbolic z plus 2 pi I, we replace z by z plus 2 pi I, equal to minus I sine I. Instead of z we have to replace z by z plus 2 pi I. So this we can rewrite as sine iz plus 2 pi times I square. Now I square is minus 1, so this we can write as minus I sine iz minus 2 pi, taking I square equal to minus 1. Now from this if we expand this by sine of alpha minus beta, or we can write this as minus I, and if I consider negative sign outside, I will have sine of 2 pi minus iz. So here negative negative positive, and we are left with I, and this I can rewrite as sine of minus iz plus 2 pi. Now sine is periodic function with period 2 pi, so sine of minus iz plus 2 pi will be equal to sine of minus iz, and sine of minus iz is nothing but minus sine of iz, because sine function is odd function, and minus I sine z is nothing but sine hyperbolic z, and this is true for all z. Our left hand side was sine hyperbolic z plus 2 pi I, and we started from sine hyperbolic z plus 2 pi I, and we obtained sine hyperbolic z for all z. So that means sine hyperbolic z is a periodic function with period 2 pi I. Similarly, you can show that cos hyperbolic z is also a periodic function with period 2 pi I.